Welcome to section 1.3, day 1, continuity and limits. Today's objectives are to use limits to determine the continuity of a function and to apply the intermediate value theorem on continuous functions. So limits and continuity. The limit. This is a concept of approaching a value without ever having to reach it. If the value of f of x approaches a unique value L as x approaches that number from both sides, some c value from both sides, then the limit of f of x as x approaches c is L. We will demonstrate this on the next slide. And we write this as limit of f of x as x approaches c equals L. And that is how we read it. The limit of f of x as x approaches c is L. We will be using limits a couple of different times this year. This is just an introductory to limits and the concept behind them. So continuity in mathematics, there's a definite definition for this. So continuous functions have no holes, breaks, or gaps. In the past, you might have heard just as long as you can draw without lifting your pen from the paper, that type of deal, but there's an actual mathematical definition. So a mathematical definition is a function f of x is continuous at x equals c for some value of c if it satisfies the following conditions. When you plug in that value of c into f of x, f of c exists. You can actually get a value back for when you plug c in. F of x approaches the same value from both sides of c. So as long as it has the same approach from both sides, that means the limit of x approaches c, f of x exists. So we have the limit exists, f of c exists, and the value that we approach from both sides is the same as f of c. So the limit as x approaches c of f of x is f of c. This is the definition. We'll show how this works on the next slide with a graph. The three things have to occur to have continuity for the mathematical definition. F of c exists, the limit at c exists, and the limit equals f of c. So infinite discontinuity. So if you look at this first graph, as we are approaching 3 from the negative side and from the positive side, we're going to say that 3 is our c. What happens is we start diving down to negative infinity from the left, and we start shooting up to infinity from the right. So in this one, there is no limit because from the left and right, it's going in opposite directions, and we have what we call an infinite discontinuity. This graph is not continuous. We cannot draw it without lifting our pen from the paper. The limits go to negative infinity and infinity, which are not the same. And f of 3 in this case, if you look at it, does not exist. There is a asymptote right here that runs through our graph. This has an infinite discontinuity. When we look at the middle graph, we have what we call a jump discontinuity. Our c in this case is at 4, and as we approach 4 from the left, we approach negative 4 from the left. The limit as x approaches 4 is negative 4. When we approach it from the right, so from the right, the limit as x approaches 4 is 2. These two do not match. We are not approaching the same thing. F of c does exist, and f of c, or f of 4, is at negative 4. These do not all match, so there's discontinuity. When you look at the picture, there's discontinuity. This is how we look at those limits, though. We're approaching 4 from the left, we're going to negative 4. We're approaching 4 from the right, we're going to positive 2. They do not match. And so we have a jump discontinuity here. It just jumps between the two sides. This would be like a piecewise function. Then we have the one on the right. We do have a discontinuity. When we look at this, we take our limit as we approach 1 from the left. We are approaching 4. If we do it from the right, the limit as x approaches 1 from the right, we're also approaching 4. Well, you'll notice there is a hole there. So f of 1 does not exist because we have a hole there. So by definition, we have to have f of 1 equal to limit from the left, limit from the right. They do not. This has a hole in, and there's a discontinuity there. This is something that we can actually fix algebraically. We will show that later on this year, but this is whenever you just have a hole and both sides approach the limits from both sides are the same, like in this case, they both approach 4, then we have a hole discontinuity and we can remove it. The other two types of discontinuity cannot be removed. There is no way to fix it algebraically. So here we have limits and continuity. First, we're going to look at the left graph, and then we'll look at the right graph. So we're going to want to see what the limit is as x approaches -1. So here's -1. We're going to come in on the x this way and then this way. So as we're coming across, we're going from left. We have f as we approach -1 is going to approach roughly -2.5. And we're approaching it from the right side. We're approaching also -2.5. So our limit is -2.5 from both left and right. Then we look at what f of -1 is. And you'll see that f of -1 is also -2.5. So what we can say is at this point right here at -1 of f of -1, we have a continuous function because f of -1 and the limit agree. Now we're going to look at the limit as x approaches 1. So from the left side, we're coming in. From the left, we're approaching -1.5. From the right, we're approaching -1.5. But if you look at f of 1, and you see where the closed circle is, f of 1 is at -4. This is not drawn there. Okay. You notice for this bottom one, right here, these do not match. That means we have a discontinuity there. So is the entire function continuous on the left one? No, it is not. Because we have a discontinuity right here. We have a hole. So it's not continuous. Now what it says here on the bottom, it says to justify continuity discontinuity, we want to use a table of values from your calculator. So we want to use a step of 0.1 or 0.01. So what you're going to do is you're going to plug this into your calculator, this function right here. And then we're going to see what happens as we approach these two, f of -1 and f of 1. We want to see what's happening to our numbers. I just need to see a couple of numbers from each side. So what I recommend is, since we're going to -1 and we're going to 1, start your table set at like -2, do an increment of 0.1, and then give me some values. So like -1.2 on your calculator, you get -1.984. At -1.1, you get a value of -2.246. And then you do the same thing for -0.9. And you're going to look at these values and see what's happening. This is equal to -2.745. And -0.8 equals -2.976. So if you look at, you have -2.246 at -1.1, and at -0.9 you have -2.745. And roughly right in between those, roughly, is -2.5. You do the same thing for the other one. Give me 4 values at x equals 1. So again, you do like at 0.8 as you're coming in from the left. You do 0.9. You do 1.1 and 1.2. And give me those values. Since it says on this that the function does not equal 1, we know that there's a hole there. But I want you to be able to look at a calculator, look at a table of values, and see what's happening. Instead of just looking at a graph, you should be able to look at a calculator table and see what's going on also. Okay, so that's the one on the left. Now we're going to look at the one on the right. I'm going to do this in green. All right, just looking at the graph, as we approach -1, from the left, we are diving down. We're going to negative infinity. As we approach it from the right, we're going to infinity. We're going really sharp up. As you'll notice, we have an asymptote right here, down at -1. So when you're looking at this, you should be able to tell right away that it's discontinuous. The limit, as we approach the left, to -1 from the left and from the right are not the same. One is going to a negative infinity, and one is going to infinity. So we have a disco right there. We already know it's discontinuous for the whole function. Now we're also going to look at the limit as x approaches 1 from the left. I'll do this in a different color. So we're approaching 1 from the left, and then we're going to approach it from the right. We approach 1 from the left, we are approaching 1. The limit as we approach from the right is also 1. So the limit as x approaches 1 is 1. We do have a limit there. We have continuity at that point. But the entire function is discontinuous because we have that infinite discontinuity at -1. So this is how we look at limits and continuity. So continuity, you're looking for both the left and the right limits to be the same as you approach some x value. They should be approaching the same y value from both sides. And you also have to verify that the function exists at that place. In your book, it will say to use a table of values to justify your continuity, discontinuity. I just need a couple of numbers on each side of where you're doing your limits to. So I can see you're pulling off of your calculator, that you can look at a calculator table and pull things. If you looked at this right graph on a table, you would see that there is nothing in there for -1. You would see an error. If you see an error in your calculator, that means there's a hole there or there is some sort of discontinuity there if you see an error. If you type this in your calculator, you would see an error at x is -1. So the intermediate value theorem, IVT, this states if f of x is a continuous function and a is less than b, and there's a value n such that n is between f of a and f of b, then there is a number c such that a less than c less than b, and f of c equals n. Well, what does that all mean? So let's say our a is right here. This is my a. Let's say this is my b. All right, a goes to -3, b goes to 4. So n is going to be some value. What it's saying is that between -3 and 0, there is going to be an n. Because we have a continuous function, and we have a -3 here, and a 0 here, we are going to have every single y value between -3 and 0. What this also states is that there is going to be some x value that goes to every single y value between -3 and 0. So let's say we wanted to go to -2. It's saying that there's some c value in here, in between a and b, where f of c is going to equal -2. There is some c value that we can find where f of c is going to be -1. This is what the intermediate value theorem says. If you have a continuous function, and we get back some y values, f of a, in this case, goes to -3, f of b goes to 0, that means we can find every y value. There's going to be some x that goes to every y value between -3 and 0. That is the gist of the IVT, the intermediate value theorem. So there's a corollary to this, the location principle corollary. So if there's a continuous function and we have opposite signs for our a and our b, let's say now, instead of our b being at 4, x equals 4, let's say we're going to do this where we're going to do b is at 6 now. So what it says is that f of a, in this case, is negative, and that f of b, in this case, is positive. So there is some place in between 0 and 6 that this crosses the x-axis, because a is negative and b is positive. So there has to be some place in between where we cross, that there has got to be at least 1 0. There could be more than one, but there has to be at least one where we have a 0. Sort of makes sense when you think about it. Continuous, we start with a negative number, go to a positive number. We must have somewhere where we change from negatives to positives. That's what this is stating. So the IVT. Using that corollary, it says determine between which consecutive integers the real zeros of each function are located on these intervals. So we're going to use a table on your calculator, use a step of 1, and we see if there are sign changes. So again, when you pull your tables up, give me some of the numbers. So f of -3, if you do it on a table, goes to -13. And when you do f of -2 on the table, you will see it goes to 2. We had a sign change. There is a 0 between -3 and -2. Somewhere between those two, we cross the x-axis. Going further on your table, you get f of 0 is 2. F of 1 is -1. And f of 2 is 2. Between these two, we go from positive to negative. So there must be a 0 somewhere between 2 and -1. And then we change signs again from -1 to 2. So we have a 0 between -1 and 2. That's all we're going to be doing on this. That's for the most part. As you look at these, pull a table up, see between which integers we have a 0. These are all continuous functions on these intervals. So if we have a sign change, we must have a 0 between them, those two values of x. Last one we have is x squared plus x plus 0.16. If you pull up a table on this, you won't find any place where the sign changes. There are no sign changes. But we also, since we have no sign changes on a table, we should still graph it, because there could be some place where it's dipping or touching the x-axis between two integers. The one we did previous, we had sign changes between the integers, we could see it. This one we're not seeing anything, so graph and see what happens. We will see if you graph this. Let's say this is -1 here. This is going to barely dip below and then come back up between 0 and -1. It barely goes below the x-axis and goes back above it between -1 and 0. So we have zeros between 0 and -1. So first, look at a table. The table will probably show your zeros. If you don't see any zeros on your table, graph it to verify. Because you could have a place where it's just touching the x-axis in an interval, or it's barely crossing it, and the crossings are between the two x values. So you aren't seeing a sign change on a table with step 1. All right, that is all for section 1.3, day 1. We looked at continuity, we looked at limits, we looked at the intermediate value theorem. Thank you for watching, and have a nice day.